Imagine staring into the night sky, where every pinprick of light is a distant sun, some already gone, their final breaths traveling across space and time just to reach your eyes. Out there, in the unimaginable vastness, stars don't just fade quietly. They explode with such fury that, for a brief moment, they outshine entire galaxies. These are supernovas, cosmic fireworks that rewrite the rules of physics and scatter the very elements that make up our world. But what if I told you some of these explosions are so far away, their light has traveled for billions of years before we even knew to look? Today, we're diving into the most distant supernovas ever discovered, stellar ghosts whose stories are written in fading light, each one a time capsule from the universe's wild youth. Think about this: when the light from these supernovas began its journey, Earth didn't even exist. Continents hadn't formed. The atoms that would become you and me were scattered across nebulae, waiting to be forged inside stars. These distant supernovas aren't just scientific curiosities. They're messengers from a time when the universe was smaller, hotter, and utterly unrecognizable. By studying them, we're piecing together the puzzle of how everything, galaxies, planets, even life itself, came to be, and the secrets they've already revealed are stranger than fiction. Some of these explosions defy what we thought possible, burning brighter than entire solar systems, or leaving behind cosmic oddities like zombie stars and black holes. So why does this matter? Because every time we spot one of these ultra-distant supernovas, it's like uncovering a page from the universe's hidden diary. Each explosion teaches us something new about how stars live, die, and shape the cosmos around them. Over the next 30 facts, we'll journey to the edge of observable space, where these ancient beacons flicker in the darkness. We'll explore how astronomers find them, what makes them so extraordinary, and why they might hold the key to understanding the fate of the universe itself. Buckle up, because we're about to travel back in time, one dazzling explosion at a time. At the heart of every supernova lies one of the universe's most spectacular acts of destruction and creation. Picture a star massive, luminous, and burning for millions or even billions of years, suddenly collapsing under its own weight. The result: a cataclysmic explosion so powerful it can briefly outshine an entire galaxy. That's a supernova, the violent end of a star's life and the beginning of something new. These explosions come in different flavors, each with its own cosmic fingerprint. Take Type 2 supernovas, for example. These are the dramatic finales of stars at least 8 times more massive than our Sun. When such a star runs out of fuel, its core collapses in a fraction of a second, triggering a shockwave that blasts the outer layers into space at incredible speeds. The aftermath: a glowing nebula rich with heavy elements, and sometimes even a neutron star or black hole left behind. Then there's Type 1, a supernova's cosmic bombs with a twist. These occur in binary star systems where a dense white dwarf siphons material from its companion until it hits a critical limit. In an instant, the entire star detonates in a runaway thermonuclear reaction, leaving nothing behind but an expanding cloud of debris. What makes these explosions so special? Their brightness is so predictable that astronomers use them as standard candles to measure distances across the universe. Without Type 1 supernovas, we'd have no way to gauge how fast space itself is expanding. But why do these stellar explosions matter beyond their jaw-dropping spectacle? Supernovas are the universe's ultimate recyclers. The iron in your blood, the calcium in your bones, even the oxygen you breathe. All of it was forged in the hearts of stars and scattered across space by these titanic blasts. Without them, planets like Earth wouldn't have the raw materials for rocks, oceans, or life itself. They are also cosmic laboratories, creating conditions so extreme that they bend the laws of physics, giving us glimpses into realms we can't recreate on Earth. Every time a supernova flares in the distant cosmos, It's not just a star dying, it's the universe whispering secrets about how everything came to be and what might lie ahead. Sometimes the most violent events in the universe become our greatest tools for understanding it. Supernovas don't just destroy, they illuminate, acting as cosmic lighthouses whose brilliance cuts through the darkest corners of space. Here's how it works. When a star explodes as a Type 1, a supernova, it reaches a peak brightness so consistent that astronomers can calculate its distance just by measuring how dim it appears from Earth. It's like knowing exactly how bright a light bulb should be. If it looks faint, you know it must be far away. This simple yet revolutionary idea transformed our ability to map the universe, turning random stellar explosions into precise yardsticks for measuring billions of light years. But these celestial beacons did more than just measure space. They revealed one of the universe's deepest secrets: dark energy. In the late 1990s, astronomers studying distant Type 1 supernovas made a shocking discovery. Instead of slowing down as the universe expanded, as everyone expected, these explosions were actually speeding up. The only explanation, some mysterious, invisible force dubbed dark energy, was pushing galaxies apart faster and faster. Without supernovas acting as cosmic mile markers, we might never have uncovered this mind-bending truth that the universe isn't just expanding, it's accelerating toward an unknown fate. What makes this even more astonishing is the scale of these measurements. When astronomers observe a supernova billions of light years away, they're not just seeing a star's death, they're capturing a moment frozen in time, a snapshot of the universe when it was half its current age. By comparing these ancient explosions to nearby ones, scientists can track how the expansion rate has changed over cosmic history, piecing together the story of dark energy's growing dominance. It's detective work on a galactic scale, with supernovas serving as both witnesses and evidence, and the implications go even further. These stellar explosions help calibrate other distance measuring techniques, like redshift and the cosmic microwave background, creating a web of measurements that cross-check each other. Without supernovas, our cosmic maps would be blurry, our timelines uncertain. They've become the gold standard for cosmic cartography, proving that even in destruction, there's illumination, a star's final act becoming a guiding light for science. Among these ancient cosmic fireworks, one stands out as the most distant we've ever glimpsed, a stellar explosion known as SNUDS-10 WIL. Its light began traveling toward us when the universe was just a toddler, barely 3.5 billion years old. To put that into perspective, when this star detonated, Earth's most complex life forms were single-celled organisms floating in primordial oceans. The light from that explosion spent a staggering 10.5 billion years crossing the cosmos before finally reaching our telescopes. What makes SNUDS-10 WIL so remarkable isn't just its distance, it's how we found it. Astronomers discovered it using the Hubble Space Telescope, combing through years of deep field images to spot this faint, fading smudge. Its redshift value, a measure of how much the universe has stretched its light during its journey, is an astonishing 1.914. That number tells us space itself has expanded so much that the light we're seeing has been stretched nearly 3 times longer than its original wavelength. It's like listening to a song played on a record that's been slowed down to a deep cosmic groan. But here's what truly boggles the mind. SNUDS-10 WIL wasn't some monstrous, record-breaking explosion. In fact, it was a relatively ordinary Type 1 supernova, the same kind we use to measure cosmic distances. That's the magic of it. This humble stellar blast became a beacon purely because of where and when it happened, a chance alignment that let its light survive the unfathomable journey across an ever-expanding universe. Studying it gives us a pristine snapshot of the early cosmos, back when the first galaxies were still taking shape, and the discoveries didn't stop there. By analyzing its light, scientists confirmed something extraordinary about the young universe. Even back then, Type 1 supernovas behaved almost exactly as they do today. That consistency across billions of years is what lets us trust these explosions as cosmic yardsticks. Every flicker of light from these distant supernovas isn't just a star's death rattle. It's a message in a bottle, telling us how the universe has grown, twisted, and evolved since its fiery beginnings. The supernova SNUDS-10 didn't just shatter distance records, it shattered our perception of time itself. When this star erupted, the universe was barely 3.5 billion years old, a fraction of its current age. To grasp just how ancient that is, think of the Milky Way, our home galaxy. While our galaxy was already taking shape back then, it looked nothing like the majestic spiral we know today. Stars were still forming at a furious pace, and the quiet, stable neighborhoods where life eventually emerged hadn't even been built. This cosmic time capsule reveals something astonishing about the early universe. Even in its youth, the ingredients for stellar explosions were already in place. The star that became SNUDS-10 likely formed from primordial gas, the unpolluted remnants of the Big Bang. Unlike modern stars, which recycle heavier elements from previous generations, this one burned pure hydrogen and helium, yet it still met the same explosive fate as its modern counterparts. That consistency is a revelation, proof that the laws of physics govern the cosmos just as rigidly billions of years ago as they do today. Here's where it gets even more mind-bending. Light from this supernova traveled for over 10 billion years to reach us, stretching as the universe expanded along the way. During that unimaginable journey, entire galaxies collided, solar systems formed, and on one tiny planet, life evolved from single-celled organisms to beings capable of pointing telescopes at the sky. All that history unfolded while SNUDS-10's light was still en route, making its arrival a kind of time travel, a direct glimpse into the universe's formative era. And the Milky Way, back then it was smaller, wilder, and far more violent. Supernovas would have been common, lighting up the young galaxy like fireflies in a summer field. But here's the twist. While SNUDS-10's light was racing toward us, the Milky Way itself was growing, merging with smaller galaxies, slowly transforming into the structured spiral we recognize. By the time that ancient light finally reached Earth, our galaxy had settled into its modern form. A cosmic irony that the oldest supernova we've seen is a messenger from a time before the Milky Way even finished growing up. This distant explosion isn't just a relic, it's a benchmark. By comparing it to younger supernovas, astronomers can track how stellar explosions have evolved over cosmic time. Did early stars die differently? Were their explosions brighter, faster, or richer in certain elements? Each answer is a clue about how the universe changed, how galaxies matured, and how the seeds for planets and life were scattered across the cosmos. SNUDS-10 isn't just a distant point of light. It's a chapter from the universe's autobiography, written in fire and time. Spotting a supernova billions of light years away isn't just about pointing a telescope at the sky. It's like trying to photograph a firefly flickering behind a foggy window from across a football field. The tools astronomers use to catch these cosmic whispers are marvels of engineering, pushing the limits of what's possible. Take the Hubble Space Telescope, for instance. Orbiting above Earth's distorting atmosphere, Hubble's sharp eyes have captured some of the most distant supernovas ever seen, including SNUDS-10. Its Wide Field Camera 3 can detect ultraviolet and infrared light, crucial for spotting explosions whose visible light has stretched into invisible wavelengths during their epic journey across the expanding universe. But Hubble isn't working alone. The James Webb Space Telescope, with its massive gold-coated mirrors and ultra-sensitive infrared instruments, is revolutionizing the hunt. Why infrared? Because the farther away a supernova is, the more its light gets redshifted, stretched by the expansion of space into longer, redder wavelengths. By the time light from the earliest supernovas reaches us, what began as visible or even ultraviolet light has shifted entirely into the infrared spectrum. Webb's ability to peer into these invisible realms lets us see explosions Hubble could only dream of, uncovering supernovas from the universe's first few billion years, a time when stars were younger, hotter, and prone to erupting in ways we're just beginning to understand. The challenges don't stop at distance, though. Finding these supernovas is like searching for a single match struck in a forest of fireworks. Astronomers use a technique called subtractive imaging, where they compare new telescope images with older ones of the same patch of sky, looking for sudden bright spots that weren't there before. But when dealing with supernovas billions of light years away, even the brightest explosions appear as faint, fleeting smudges. Atmospheric turbulence, cosmic dust, and the sheer volume of stars and galaxies in the frame create a needle in a haystack problem. That's why projects like the Hubble Frontier Fields and Webb's Deep Field surveys focus on gravitational lensing using massive galaxy clusters as natural magnifying glasses to bend and amplify the light from even more distant supernovas hidden behind them. And then there's timing. Supernovas fade fast. Within weeks or months, even the most brilliant explosion dims to near invisibility, which means telescopes have to be looking at the right place at the right time, often by sheer luck. Programs like the Supernova Cosmology Project automate the search, using algorithms to scan telescope data for telltale spikes in brightness. But confirming a distant supernova requires follow-up observations with spectrographs, which break the light into a rainbow of colors to reveal the chemical fingerprints of the explosion. Every step is a race against time, with astronomers working around the clock to extract every possible clue before the light vanishes forever. What's truly remarkable is how these tools don't just find supernovas, they decode their stories. By analyzing the light's intensity, color, and how it changes over time, scientists can determine the supernova's type, distance, and even what elements it scattered into space. Each observation is a piece of a puzzle, helping us map the universe's expansion, test the laws of physics across cosmic time, and glimpse the conditions that gave rise to galaxies like our own. These telescopes aren't just cameras, they're time machines, turning faint glimmers from the distant past into keys for unlocking the universe's deepest secrets. Gravity doesn't just pull, it magnifies. One of the most astonishing tricks the universe plays is using entire galaxy clusters as cosmic magnifying glasses, warping space so dramatically that light from impossibly distant supernovas bends around them, giving us a front-row seat to explosions we'd otherwise never see. This phenomenon, called gravitational lensing, is like nature's ultimate zoom lens, distorting and amplifying the light of ancient stellar deaths that should have faded into oblivion billions of years ago. Take the supernova nicknamed Gravitational, for example. It wasn't just distant, it was a cosmic mirage, appearing multiple times in the same image thanks to a massive galaxy cluster bending its light like a funhouse mirror. Einstein's theory of relativity predicted this effect over a century ago. That massive objects warp spacetime so severely, they create natural telescopes far more powerful than anything we could build. But even he might have been stunned to see it in action. When Gravitational's light reached us after 9 billion years, it wasn't in one place, it was smeared into 4 separate images, forming a glowing Einstein cross around the cluster's core. Astronomers didn't just witness one supernova, they saw the same explosion at different moments in time, thanks to light taking slightly different paths around the lens. Then there's the SNHFF14 TOM supernova, magnified 30 times by the Frontier Fields galaxy cluster. Without that gravitational boost, its light would have been too faint for even Hubble to detect. But the cluster's immense gravity acted like a spotlight, bending spacetime so sharply that the supernova appeared brighter and lingered longer in our telescopes, giving scientists an unprecedented look at the chemical makeup of a star that died when the universe was a third of its current age. The real magic of lensing lies in what these distorted snapshots reveal. By studying how the light bends, astronomers can map the invisible dark matter tangled within these galaxy clusters, matter that emits no light but tugs on space-time with its gravity. Every lensed supernova becomes a tool for probing the universe's hidden scaffolding, exposing where dark matter clumps and how it shapes the cosmos. And sometimes the universe delivers an encore. After Riefstahl's initial appearance, scientists calculated when another copy of the explosion would arrive, and in 2015, right on schedule, the final flicker of that same supernova blinked into view, a delayed replay proving just how precisely we can decode the universe's warped geometry. These lensed supernovas are more than just lucky breaks, they're cosmic cheat codes. Without them, we'd be blind to entire chapters of stellar history, missing the explosions that shaped the early universe. They transform faint whispers into shouts, letting us eavesdrop on the deaths of stars so old their light predates planets' life, even the Milky Way's spiral arms. And with the James Webb Telescope now peering even deeper into these gravitational funhouses, who knows what other flickering ghosts from the cosmos's youth are waiting to be unmagnified from the dark. Every time astronomers catch the faint glow of a distant supernova, they're not just observing a stellar explosion, they're opening a window into the universe's past. It's like finding an ancient letter sealed in cosmic amber, its words written in light that's traveled across billions of years. Take the supernova SN 1995K, for instance. When its light reached Earth, we weren't just seeing a star's death, we were witnessing an event that occurred when the universe was half its current age, a time when galaxies were smaller, denser, and brimming with young, volatile stars. This time travel trick works because light doesn't arrive instantly. Even at its incredible speed, crossing cosmic distances takes eons. When we detect a supernova 10 billion light-years away, we're seeing it as it looked 10 billion years ago. The light that hits our telescopes today began its journey long before Earth formed, carrying with it a snapshot of the universe's youth. Imagine if every star in the sky was a historical document, and supernovas were the boldest, brightest passages flare up so intense they cut through the fog of time. But the real magic lies in what these explosions reveal about the early universe. By analyzing their light, scientists can measure the chemical makeup of ancient stars, discovering that the earliest supernovas spread heavier elements like iron and calcium far sooner than we once thought. These elements weren't just forged in later generations of stars. They were already seeding young galaxies billions of years ago, setting the stage for planets and eventually life. The colors and intensity of a supernova's light also tell us about the space it traveled through, revealing how the universe's expansion has stretched and twisted over time. Here's where it gets even more fascinating. Comparing distant supernovas to nearby ones lets astronomers track how stellar explosions have evolved. Were early supernovas more energetic? Did they produce different elements? The answers are written in the light we capture today, each explosion a data point in the universe's growth chart. And with tools like the James Webb Telescope peering deeper than ever, we're not just glimpsing the past, we're rewriting the story of how everything came to be. Every flicker from these cosmic time machines is a puzzle piece, helping us assemble a portrait of the universe's wild, explosive childhood. Finding a supernova billions of light-years away is like winning the cosmic lottery, not just because of the staggering distances involved, but because the universe plays brutal odds against us. For every distant supernova we've discovered, countless others flicker into oblivion unnoticed, their light stretched too thin by expanding space or drowned out by the glare of nearer galaxies. Even with our most powerful telescopes, fewer than 24 supernovas have been confirmed at redshifts greater than 2, meaning their light has traveled for over 10 billion years before reaching us. Consider the math for a moment. At these extreme distances, a supernova's light spreads out over such a vast area that by the time it reaches Earth, only a handful of photons, actual particles of light, hit each square meter of our telescope's detectors every second. That's like trying to spot a single candle flickering on the moon. Adding to the challenge, these explosions are fleeting. A supernova might blaze brilliantly for weeks, but in the grand timeline of the universe, that's less than the blink of an eye. Miss that narrow window, and the event vanishes from observable history forever. Then there's the sheer volume of space to search. Imagine scanning every grain of sand on every beach on Earth, looking for one specific grain that glows for a minute before fading. That's the scale astronomers contend with when hunting distant supernovas. Even Hubble's deep field images, which stare at tiny patches of sky for days, capture only a fraction of the possible explosions happening out there. The rest slip through the cracks, their stories lost to the darkness. Yet against these impossible odds, we've still managed to catch a few. Each discovery is a triumph of technology and persistence, like SN 1997 FF, found in Hubble's deep field data after painstaking analysis, or SN 2015 L, whose faint infrared glow was teased out by the James Webb Telescope after other observatories missed it entirely. These rare finds aren't just scientific victories, they're reminders of how much we're missing. For every ancient supernova we detect, thousands more remain hidden, their light still traveling toward us or already faded beyond recovery. What makes these discoveries so precious is their scarcity. Each one gives us a unique data point in the universe's expansion history, a clue about how stars lived and died when the cosmos was young. And with new telescopes pushing further into the infrared, where the most distant supernovas hide, we're finally starting to tilt the odds in our favor, peering deeper into the past than ever before, one improbable flicker of light at a time. The brilliance of a supernova doesn't fade, it gets stretched. When a star explodes billions of light years away, its light doesn't simply dim like a dying ember, it's pulled apart by the expanding universe itself. Picture a flashlight beam crossing a rubber sheet that's being stretched in all directions. The light spreads thinner, redder, and weaker by the time it reaches us. That's why a supernova that might have outshone its entire galaxy at the moment of explosion appears as nothing more than a faint speck in our telescopes. But here's where things get counterintuitive. That dimness is actually a goldmine for astronomers. Take two supernovas of identical intrinsic brightness, one exploding relatively nearby, the other at the edge of the observable universe. The farther one will look dramatically fainter, not just because of distance, but because its light has been stretched by cosmic expansion. This stretching, called redshift, transforms visible light into infrared, pushing some of it entirely out of detectable range. A supernova that dazzled with blue-white fury at its origin might reach us as a feeble infrared glow, barely distinguishable from the background noise of the cosmos. So how do scientists compensate for this cosmic dimming act? First, they rely on the fact that certain supernovas, like Type 1a, are standard candles, explosions with a known, consistent peak brightness. By measuring how much dimmer they appear than expected, astronomers can calculate exactly how much the universe has stretched their light, like tracking how much a song slows down on a warped record. Tools like the Hubble and James Webb telescopes are calibrated to catch these redshifted whispers, using sensitive infrared detectors to spot what human eyes could never see. But it's not just about better cameras. Astronomers apply meticulous corrections for interstellar dust, which further scatters and reddens light, and they account for the time dilation predicted by Einstein, where the supernova's light appears to fade slower from our perspective because the expanding universe stretches time itself. It's a cosmic balancing act. The dimmer the supernova, the more its light has been altered by the journey, and the more it reveals about the universe's expansion history. This painstaking work turns what seems like a drawback, the faintness of distant supernovas, into a precision tool. Every photon that makes it to our telescopes carries clues about the space it traversed. By comparing nearby and faraway supernovas, we're not just measuring distances, We're mapping how the universe's expansion has accelerated over billions of years, uncovering the invisible forces shaping our cosmic fate. The dimmest points of light, it turns out, shine the brightest on the grandest questions. Every breath you take contains atoms forged in stellar explosions. That iron in your blood, the calcium in your bones, even the gold in your jewelry, none of it would exist without supernovas scattering their elemental ashes across the cosmos. When a massive star reaches the end of its life and detonates, it becomes a cosmic alchemist, transforming simple elements into the building blocks of planets and life itself. The temperatures and pressures inside these explosions are so extreme that they can fuse atoms into forms impossible under normal stellar conditions, creating everything from the oxygen we breathe to the uranium that powers nuclear reactors. Consider iron, the element that makes our blood red and our skyscrapers strong. Inside an aging star, fusion reactions create lighter elements like carbon and oxygen, but iron is different. It marks the end of the line for stellar fusion. Trying to fuse iron actually absorbs energy instead of releasing it. So when a star accumulates too much iron in its core, the fusion engine sputters out, triggering a catastrophic collapse and subsequent explosion. That's why supernovas become iron factories. Their violent shock waves and neutron-rich environments force atomic nuclei together, forging iron and even heavier elements in seconds. But the stellar alchemy doesn't stop there. Elements like gold, platinum, and uranium require even more extreme conditions, so extreme that scientists now believe they form primarily in the aftermath of colliding neutron stars, which are themselves remnants of supernovas. These rare cataclysmic mergers blast neutron-rich material into space at incredible speeds, creating a rapid capture process that builds ultra-heavy atoms. Over billions of years, these elements get incorporated into interstellar clouds, eventually becoming part of new stars, planets, and even living organisms. Here's what's truly humbling: the carbon in your DNA, the iron in your blood cells, and the iodine in your thyroid all originated in different supernovas that exploded at different times across the galaxy. Our solar system formed from a cloud of gas and dust enriched by generations of these stellar explosions, meaning every atom in your body, every atom on Earth, is truly stardust recycled through multiple cosmic cycles. Without supernovas scattering these heavy elements into space, planets like ours would lack the raw materials for continents, oceans, or complex chemistry. Life as we know it literally wouldn't have a leg to stand on. This chemical legacy explains why astronomers study supernova remnants so intensely. By analyzing the elements present in these expanding clouds of debris, we can trace which stars produced which elements and how they spread through the galaxy. Some remnants, like Cassiopeia A, are veritable periodic tables of heavy elements, glowing with the telltale signatures of silicon, sulfur, and argon. Others reveal unexpected abundances, hinting that certain types of supernovas might specialize in creating specific elements. Each explosion contributes a unique mix to the cosmic inventory, slowly enriching the universe with the ingredients for new worlds and perhaps new life. So the next time you look up at the night sky, remember, those twinkling lights aren't just distant suns. They're future element factories brewing the materials that will one day become part of planets, mountains, and maybe even beings who will gaze back at the stars, wondering about their own origins. Supernovas don't just destroy, they create, leaving behind a legacy written in the very atoms that make up our bodies and our world. Supernovas don't just end stellar lives, they spark new ones. Imagine a shockwave racing through space at millions of miles per hour, slamming into nearby clouds of gas and dust with enough force to crush them into dense knots. That's how a star's death becomes the cradle for its successors. When a supernova explodes, its titanic blast doesn't just scatter elements, it compresses surrounding materials so violently that gravity takes over, pulling these clumps together until nuclear fusion ignites deep within them. This cosmic domino effect means every dying star can plant the seeds for hundreds more, turning destruction into creation on a galactic scale. One of the most stunning examples lies in the Orion Nebula, where astronomers have traced young stars back to shockwaves from ancient supernovas. The nebula's vibrant stellar nursery, glowing with newborn stars, owes its existence to explosions that occurred long before humans walked the Earth. These shockwaves didn't just nudge gas clouds, they sculpted them, carving intricate structures and triggering collapses that would have taken billions of years to happen naturally. It's like tossing a boulder into a still pond and watching the ripples transform into towering waves that rearrange the shoreline. But the process isn't just about brute force. Supernova remnants enrich these star-forming regions with heavy elements, creating the perfect chemical cocktail for planet building. The dust clouds that collapse under these shockwaves aren't just hydrogen and helium anymore, they're peppered with carbon, oxygen, and iron, the raw materials for rocky worlds and organic molecules. Some scientists even suggest our own solar system might owe its existence to a nearby supernova's kickstart, its shockwave jump-starting the collapse of the molecular cloud that birthed the Sun. And the cycle doesn't stop there. The new stars born from these ashes will eventually explode themselves, sending out fresh shockwaves to ignite future generations. This self-perpetuating loop where death fuels birth, which in turn leads to more death, has been shaping galaxies since the universe's earliest days. In distant galaxies, astronomers have spotted starburst regions where supernova-triggered star formation runs rampant, creating dazzling fireworks of stellar birth and death. These cosmic recycling plants operate on timescales almost impossible to grasp, turning destruction into the very engine of cosmic evolution. What's truly remarkable is how finely tuned this process is. Too weak a shockwave and the gas just wobbles back into place. Too strong and it blows the cloud apart entirely. Supernovas hit that Goldilocks zone with eerie precision, their energy perfectly calibrated to collapse clouds without obliterating them. It's as if the universe encoded a recipe for balance into these explosions, one that ensures stars die not with a whimper, but with a bang loud enough to keep the cosmic story going. When a supernova explodes, the debris doesn't just drift away, it rockets outward at speeds that defy comprehension. Take the Crab Nebula, the remnants of a star that lit up the sky in the year 1054. Today, its shattered remains are still racing outward at nearly 1,500 kilometers per second, fast enough to cross the continental United States in less than 3 seconds. That expansion isn't slowing down either. The nebula's delicate filaments and swirling plasma continue pushing against interstellar space, growing visibly larger even within a human lifetime. Astronomers have measured its growth by comparing photographs taken decades apart, watching as this cosmic wreckage stretches farther and farther into the void. But here's where distant supernovas tell a different story. When we observe remnants from explosions billions of light-years away, their expansion appears dramatically slower, not because they're moving less violently, but because of the mind-bending effects of cosmic expansion. Imagine watching a sprinter on a treadmill that's rolling backward at nearly the same speed they're running forward. From your perspective, they'd seem to inch forward sluggishly, even though they're straining at full tilt. That's what happens with ultra-distant supernovas. Their shockwaves might be racing outward at tens of thousands of kilometers per second, but the stretching of space itself dilutes their apparent motion, making them seem almost frozen in time. This illusion holds vital clues about the universe's structure. By comparing how fast nearby remnants like the Crab Nebula expand versus their ancient counterparts, astronomers can track how the fabric of space has changed over cosmic epochs. Some distant supernova remnants appear to expand slower than physics predicts, hinting that the early universe's higher density of matter and dark energy might have subtly resisted their outward push. Others show strange asymmetries, their debris flying faster in one direction, evidence of turbulent magnetic fields or uneven explosions that modern telescopes are only now revealing. The real surprise, even these ancient remnants aren't done evolving. Light from the most distant supernovas takes so long to reach us that we're effectively watching them in slow motion. A remnant that appears static in our images might, from its own perspective, have already swept up enough material to form new stars or trigger fresh rounds of cosmic chemistry. Time and space conspire to stretch these explosions into celestial time lapses, giving us a front-row seat to events that, were we closer, would blaze by in the blink of an eye. So whether it's the Crab Nebula's relentless march or a distant remnant's cosmic slow dance, each supernova's expansion tells a dual story: the raw power of a star's final moments and the universe's subtle fingerprints on how that power unfolds across the ages. These exploding stars don't just leave behind beautiful nebulae, they leave behind speedometers, clocks, and yardsticks that measure the cosmos itself. In the late 1990s, astronomers made a discovery so shocking it upended everything we thought we knew about the universe's fate. They were studying distant Type 1, a supernova's stellar explosions so predictable in brightness that they serve as cosmic mile markers, when they noticed something impossible. Instead of appearing slightly brighter than expected, as the prevailing theory predicted, these ancient supernovas were fainter, as if someone had turned down a dimmer switch across the cosmos. The only explanation: the universe wasn't just expanding, it was accelerating, pushing galaxies apart faster and faster over time. This revelation, earned by painstaking observations of supernovas billions of light-years away, led to the Nobel Prize-winning discovery of dark energy, a mysterious force that makes up 68% of the universe and operates as cosmic anti-gravity, stretching space itself apart. What makes this breakthrough even more astonishing is how it hinged on supernovas from opposite ends of cosmic history. By comparing nearby explosions whose light reached us after just millions of years, with those that detonated when the universe was half its current age, scientists could track how expansion rates changed over billions of years. The pattern was undeniable. Ancient supernovas showed slower recession speeds than modern ones, proving expansion wasn't slowing due to gravity as expected, but speeding up. Imagine throwing a ball in the air only to watch it shoot away faster instead of falling back. That's the level of cosmic defiance dark energy represents. The implications ripple across physics. Dark energy's dominance means the universe will likely expand forever, growing colder and emptier as galaxies drift beyond each other's horizons. But its nature remains one of science's greatest mysteries. Is it Einstein's cosmological constant, an inherent energy of space itself, or something more exotic like a dynamic field that changes over time? Distant supernovas remain our best tool for probing these questions. Their light, stretched by the universe's expansion, carries encoded clues about how dark energy's strength has evolved. Recent observations of supernovas even farther back in time suggest dark energy might not be constant after all, hinting at physics beyond Einstein's theories. This revelation didn't just come from a single eureka moment. It was the culmination of two competing teams, the Supernova Cosmology Project and the High-Z Supernova Search, independently scrutinizing hundreds of stellar explosions across billions of light-years. Their rivalry sharpened the science, with each group double-checking the other's measurements of supernova brightness, distances, and redshifts, when both reached the same terrifying conclusion: that the universe was flying apart under some unseen influence. Even the researchers struggled to believe it. As astronomer Saul Perlmutter, who shared the 2011 Nobel Prize for the discovery, later admitted, "We kept expecting someone to find a mistake in our work." But the supernovas didn't lie. Now, next-generation telescopes like the Vera Rubin Observatory are preparing to scan thousands more distant supernovas, searching for subtle variations in dark energy's push. Some theories suggest its strength may have fluctuated over cosmic history, leaving fingerprints in the light of ancient stellar explosions. Others propose it interacts differently with matter across vast distances, an effect only detectable by comparing supernovas from multiple epochs. Whatever these dying stars reveal next, one thing is certain. Without their fleeting brilliance illuminating the darkness, we'd still be oblivious to the invisible force shaping the universe's ultimate fate. The most profound truth of modern cosmology was written in the ashes of exploded stars, deciphered by those patient enough to listen to whispers from the abyss. The light from distant supernovas doesn't just fade, it transforms. As these explosions race away from us across an expanding universe, their light stretches like taffy, shifting from brilliant blues and whites to deep reds and eventually into the infrared, far beyond what human eyes can see. This phenomenon, called redshift, isn't just a quirk of physics, it's the universe's way of tattooing its history onto starlight. The farther a supernova is, the more space has stretched during its light's journey, and the more its colors slide toward the red end of the spectrum. It's as if the cosmos itself is tuning a cosmic radio dial, lowering the pitch of ancient starlight until only the deepest notes remain. Take a supernova that erupted when the universe was half its current age. By the time its light reaches us, what began as ultraviolet radiation invisible to our eyes but detectable by telescopes, might now appear as visible red light. For even more distant explosions, that same ultraviolet glow could stretch all the way into the infrared, a wavelength range where only specialized instruments like the James Webb Space Telescope can spot it. This color shift isn't just dramatic, it's measurable. Astronomers quantify it using a number called Z, where higher values mean greater stretching. A supernova with a redshift of 1.5, for example, has had its light waves stretched by 150%, meaning the light we see left its source when the universe was just 2.8 billion years old. But redshift isn't just about distance, it's a time machine. When we catch the reddish glow of a high Z supernova, we're not just seeing an explosion far away, we're witnessing how it looked billions of years ago, frozen in light that's been stretched by the universe's expansion. The color itself encodes the explosion's age like rings in a tree trunk. By comparing the redshift of multiple supernovas, astronomers can map how quickly space has expanded over cosmic history, revealing when dark energy began to dominate gravity's pull. Here's where it gets even more fascinating. Different elements in a supernova's debris leave distinct chemical fingerprints in its light called spectral lines. In nearby supernovas, these lines appear at predictable wavelengths, say, a spike of blue light from ionized silicon. But in distant supernovas, those same lines show up shifted toward redder hues like a song played at half speed. By measuring how much these lines have moved, scientists can calculate not just the supernova's distance, but also how fast its host galaxy was speeding away when the explosion occurred. It's a cosmic Doppler effect where the stretching of light becomes a speedometer for the universe's expansion. This color coding of cosmic history has led to some astonishing discoveries. For instance, supernovas with redshifts greater than 2 often appear redder than expected, hinting that the early universe expanded differently than it does today. Some show spectral lines so stretched they're nearly unrecognizable, requiring astronomers to reconstruct their original tune from the slowed-down version that reaches us. And because redshift affects all light equally, from the explosion's initial flash to its fading embers, it even alters how quickly the supernova appears to fade from our perspective. A 2-month-long explosion might seem to stretch over 3 months in our telescopes, its timeline warped by the universe's expansion like a film played in slow motion. Yet for all its complexity, redshift remains one of astronomy's most powerful tools. Without it, we'd have no way to gauge the true vastness of the cosmos or trace its evolution across billions of years. Every reddened photon from a distant supernova is a puzzle piece, helping us assemble a picture of where the universe has been and where it's hurtling next. The colors of these cosmic explosions aren't just pretty details, they're the brushstrokes painting the grandest portrait of all, the story of space and time itself. A supernova's brilliance is fleeting by cosmic standards. What seems like an eternal beacon to us is really just a stellar flash in the pan. From the moment a star explodes, its visible light typically peaks within days or weeks, then gradually fades over months. But that timeline isn't fixed. The duration of a supernova's glow depends on its type, the elements it ejects, and even the angle at which we observe it. Take a classic Type II supernova. The initial blast floods space with light as the shockwave heats surrounding gas to millions of degrees, creating a blinding flash. But as the expanding debris cools and thins, the visible light dims, often disappearing from amateur telescopes within a year. Distant supernovas, however, play by different rules. When we spot an explosion billions of light years away, we're usually catching it weeks or months after its peak brightness, not because the light traveled slowly, but because the universe's expansion stretches time itself. Imagine watching a video call with terrible lag. The person on screen might be waving in real time, but their movements reach you delayed and sluggish. Similarly, a supernova that blazed for 100 days in its own frame might appear to flicker for 200 days from our perspective, its timeline stretched by the expanding space between us. This time dilation means astronomers often study these cosmic explosions in what's essentially slow motion, observing details in fading light that would have been a blur during the initial outburst. But there's another twist. Distance filters out the flashy beginning. The farther away a supernova is, the more its initial peak gets diluted by the vastness of space. By the time that light reaches us, only the lingering afterglow, the slow fade of cooling debris, may still be bright enough to detect. It's like trying to spot a firework from miles away. You'll likely miss the initial burst but might catch the glowing embers drifting down. That's why Hubble and Webb often discover ancient supernovas in their twilight phases, their light already fading from a climax we'll never witness. Yet this fading light holds treasures of its own. As a supernova dims, its spectrum changes, revealing layers of ejected material like the rings of a tree. The longer we observe, the deeper we see into the explosion's heart, tracing elements like oxygen, silicon, and iron that were forged in the star's final moments. Some supernovas even experience light echoes, where their illumination bounces off interstellar dust, creating ghostly afterimages that linger for years. These delayed signals act like cosmic strobe lights, illuminating structures in space we'd otherwise never see, proof that even in death, a star's story isn't told all at once, but in chapters written across centuries. So while a supernova's visible glow may be brief, its legacy unfolds far longer. From the initial shockwave to the final whispers of infrared radiation, these explosions refuse to fade quietly. They transform, adapt, and reveal new secrets at every stage, whether we catch them in their dazzling prime or their quiet aftermath. The most distant supernovas aren't just explosions, they're time capsules from the era when galaxies were taking their first breaths. Picture the early universe, a seething cauldron of hot gas, dark matter, and fledgling stars, all swirling in the dark. In this primordial chaos, the first galaxies were nothing like the majestic spirals we know today. They were smaller, messier, and far more violent, packed with young, unstable stars that lived fast and died furious. Every supernova that erupted in those early epochs didn't just light up the darkness, it shaped the very fabric of its host galaxy, blowing away loose gas, triggering new star formation, and seeding space with heavy elements. Take the galaxy GN11, one of the most distant ever observed. When astronomers spotted a supernova remnant within it, they weren't just seeing a stellar explosion, they were witnessing a construction site. The blast shockwave would have compressed nearby gas clouds, jump-starting the birth of future stars while scattering metals forged in the dying star's core. These metals, elements heavier than hydrogen and helium, were the universe's first building blocks for rocky planets and eventually life. Without these early supernovas, galaxies might have remained sterile hydrogen blobs forever. But the influence went both ways. The conditions in these infant galaxies made their supernovas behave strangely. Denser gas clouds meant shockwaves traveled differently, sometimes stalling before they could escape the galaxy's gravity. Younger stars made of purer hydrogen and helium likely exploded with different chemical signatures than modern supernovas. By studying the light from these ancient blasts, astronomers have found surprising hints like higher proportions of certain isotopes or faster fading times that suggest the first stars didn't just die, they died differently, leaving behind fingerprints of a universe still figuring out its own rules. One of the most tantalizing clues comes from paired supernovas and gamma-ray bursts. In today's universe, these ultra-energetic events are rare, linked only to the most massive stars. But in the early cosmos, they might have been commonplace, lighting up young galaxies like cosmic flashbulbs. Some theorists argue that the first stars were so massive, hundreds of times the sun's weight, that their deaths weren't mere explosions but apocalyptic hypernovas, blasting jets of material at near light speed. These jets could have pierced through their host galaxies, carving out channels where future stars would form and injecting energy into the intergalactic void. The echoes of these cataclysms are still detectable today. When we observe distant supernovas nestled inside ancient galaxies, we're seeing the aftermath of explosions that might have dictated their host's fate, whether it became a quiescent elliptical or a star-forming spiral. Their light carries traces of the gases they expanded into, revealing how tightly packed early galaxies were or how fiercely their black holes heated surrounding material. Some supernovas even show signs of interacting with previous generations of explosions, their debris slamming into older remnants like waves crashing on a shore. What's emerging is a picture of chaos and creativity. The first galaxies weren't passive backdrops for supernovas. They were shaped by them, their evolution steered by each successive wave of stellar death. Every explosion enriched their chemistry, stirred their gases, and in some cases blew away so much material that star formation sputtered out entirely. It's a dance of creation and destruction that's still playing out today, but with far quieter footsteps. By studying these distant supernovas, we're not just reconstructing the past, we're uncovering the blueprint for how galaxies like our own Milky Way grew up, one violent, brilliant explosion at a time. A supernova might be the ultimate silent movie, a cataclysm so violent it tears apart solar systems, yet utterly soundless in the vacuum of space. But if we could hear it, the soundtrack would shatter every volume record. Picture this: the initial shockwave rips through the dying star's outer layers at over 30,000 kilometers per second, a wall of plasma so dense it could crush atoms into neutrons. That shock doesn't just travel, it rings the star like a bell, vibrating at frequencies that, if translated to sound, would produce a bass note deeper than anything audible to humans. We're talking about oscillations so low they'd register more as seismic tremors than noise, pulsing through space like the world's slowest, heaviest drumbeat. Yet this cosmic symphony isn't entirely lost to silence. While space itself has no medium for sound waves, the supernova's shockwave does something extraordinary as it plows through surrounding gas clouds. Imagine throwing a boulder into a pond, except the pond is made of superheated plasma, and the ripples are pressure waves detectable by radio telescopes. These waves don't produce audible sound, but they create oscillations in the interstellar medium that mirror the structure of music. When astronomers analyze the radio emissions from supernova remnants like Cassiopeia A, they can mathematically translate these vibrations into soundscapes. The result, a haunting, rumbling drone that drops octaves as the shockwave decelerates, like a foghorn fading into the abyss. Here's where physics gets surreal. In the star's final milliseconds before collapse, its core becomes so dense that protons and electrons merge into neutrons, releasing a neutrino burst carrying away 99% of the explosion's energy. If neutrinos were sound waves, this single pulse would outshine the entire electromagnetic spectrum, a bark so loud it'd dwarf every noise ever made on Earth combined. Instead, these ghostly particles slip through planets unnoticed, their sound existing only as mathematical models spinning inside supercomputers. But the true marvel lies in how these silent vibrations shape the cosmos. The shockwave's pressure patterns sculpt nearby nebulae, imprinting ripples that linger for millennia. Some astronomers compare it to a phonograph needle etching grooves onto a galactic record. Except the music is the birth cry of new stars triggered by the shock's passage. Even the expanding debris shell acts like a speaker cone, pushing against interstellar gas and creating standing waves that subtly heat the surrounding medium. That means every supernova hums its own unique frequency into the void, a fingerprint of destruction that quietly tweaks the universe's background temperature. So while no human ear will ever catch the roar of a dying star, its vibrations still resonate across light years, not as sound, but as invisible ripples rewriting the architecture of space itself. The universe may be silent, but it's never truly still. Every explosion leaves behind a hum, etched into the fabric of reality, waiting for instruments sensitive enough to listen. If our sun spent its entire 10 billion-year lifespan shining at full power, the total energy it would release wouldn't even come close to the raw fury unleashed in a single second by a supernova. Picture this: when a massive star collapses, the explosion can blast out as much energy as our sun radiates over 10 billion years, and it does so in less time than it takes to snap your fingers. That's not just power, that's the universe flexing its muscles on a scale that defies human intuition. To put numbers to the spectacle, a typical supernova releases around 10 to the 44 joules of energy. That's a 1 followed by 44 zeros, a number so vast it dwarfs anything we encounter on Earth. For comparison, the most powerful nuclear weapon ever detonated, the Tsar Bomba, released roughly 210 petajoules of energy. A supernova outshines that by a factor of 10 octillion. Let that sink in. One stellar explosion equals 10 billion trillion Tsar bombas detonating simultaneously. It's like comparing a firecracker to the Big Bang, but raw energy is only part of the story. A supernova's brilliance isn't just about quantity, it's about concentration. While the sun dutifully spreads its energy output across millennia, a supernova crams that same cosmic wattage into days or weeks, unleashing a flash so intense it can briefly outshine entire galaxies. At peak luminosity, some supernovas reach absolute magnitudes of -20, meaning if one occurred as close as Alpha Centauri, it would shine brighter than a full moon in our sky, casting shadows on Earth even in broad daylight. Here's where the physics gets even wilder. Most of that energy doesn't even come from the visible explosion. 99% escapes as neutrinos, ghostly particles that stream outward at nearly the speed of light. In 1987, when supernova 1987A erupted in the Large Magellanic Cloud, neutrino detectors on Earth caught a fleeting whisper of these particles. Though just 24 were recorded, their arrival confirmed a staggering truth. In that single event, the dying star had released more neutrinos than there are stars in the observable universe. And the fallout, a supernova's shockwave doesn't just fade away, it travels for millennia, plowing through interstellar gas at thousands of kilometers per second. The Crab Nebula's shock front still glows today, nearly 1,000 years after the original explosion. Its tangled filaments radiating X-rays and gamma rays with enough energy to power entire constellations. That lingering fury is why supernovas aren't just fireworks, they're cosmic engines, converting stellar death into the raw materials for new stars, planets, and even life itself. The energy might fade, but its impact echoes across the cosmos forever. When a massive star reaches the end of its life and explodes as a supernova, it doesn't always vanish without a trace. Instead, the star's core, the dense, searing hot engine that once powered nuclear fusion, can collapse into one of the universe's most extreme objects, a neutron star. Picture squeezing 1.5 times the mass of our Sun into a sphere no wider than Manhattan. The result is matter so dense that a single teaspoonful would weigh 1 billion tons on Earth, its atoms crushed into a sea of neutrons so tightly packed they behave like a single, monstrous atomic nucleus. These cosmic leftovers come in 2 spectacular flavors. First, there's the classic neutron star, a rapidly spinning, city-sized magnet with a gravitational field 100 billion times stronger than Earth. Then there are pulsars, neutron stars that beam radiation from their magnetic poles like interstellar lighthouses. As they spin, these beams sweep across space, and if aligned with Earth, we detect them as precise, clock-like pulses of radio waves or X-rays. The Crab pulsar, born from a supernova observed in 1054, spins 30 times per second, flashing so regularly that its pulses were initially mistaken for extraterrestrial signals. But neutron stars born in the early universe might have played by different rules. Back when galaxies were young and stars formed from pristine hydrogen and helium, collapsing cores could have spun faster and generated stronger magnetic fields than their modern counterparts. Without heavier elements to sap energy through radiation, these primordial neutron stars might have retained more of their initial rotation, becoming hyperactive pulsars spinning hundreds of times per second. Some theorists even suggest the first neutron stars could have been magnetars on steroids, objects with magnetic fields 1,000 times more powerful than today's most extreme examples, capable of stripping atoms apart from halfway across a galaxy. Here's where ancient supernova remnants become cosmic time capsules. When astronomers study neutron stars in distant, metal-poor galaxies' environments resembling the early universe, they've spotted puzzling differences. Some spin faster or shine brighter in X-rays than expected, hinting at formation processes we don't fully understand. Others, like the pulsar in the globular cluster Terzan 5, exhibit bizarre glitches where their rotation suddenly speeds up, as if a hidden reservoir of superfluid neutrons inside them suddenly unlocked. These quirks might be echoes of the universe's wild youth, when physics operated under conditions we can't replicate even in our most advanced labs, and the stakes are higher than just stellar oddities. Neutron stars are nature's ultimate particle accelerators, their crushing gravity and magnetic fields creating environments where matter warps into exotic states. Quark-gluon plasma, superfluids that flow without friction, even hypothesized strange matter that could infect normal atoms. These phenomena might have been more common in neutron stars forged by the earliest supernovas. Studying them isn't just about dead stars, it's about probing the limits of physics itself, using the cosmos as our laboratory. So the next time you hear about a distant supernova, remember, its flash might fade in weeks, but its legacy could endure for billions of years as a spinning, magnetic tombstone, a silent witness to the violent birth of the elements, the evolution of galaxies, and the unrelenting creativity of a universe that turns destruction into something new. Nearly 1,000 years before telescopes, in the summer of 1054, Chinese astronomers spotted something astonishing: a guest star, blazing in the constellation Taurus, so bright it was visible even during daylight for 23 days. This wasn't a comet or a planetary alignment, it was a supernova, the violent death throes of a massive star now immortalized as SN 1054. The records from China's Song dynasty describe it with poetic precision. Yellow in color, emanating pointed rays in all directions, while Japanese observers noted its brilliance rivaled Jupiter. Even halfway across the world, indigenous petroglyphs in the American Southwest may depict the same celestial visitor, a fleeting beacon that captivated civilizations with no knowledge of stars or galaxies beyond what their eyes could see. Fast forward to today, where our tools have transformed from naked eye observations to space telescopes that capture supernovas billions of light years away. The Crab Nebula, the glowing wreckage of SN 1054, is now a textbook example of a supernova remnant, studied with instruments that dissect its light into spectra, measure its magnetic fields, and even detect the spinning neutron star at its heart. Compare that to Hubble's discovery of SN JWST, a supernova so distant its light spent 10.5 billion years reaching us. Ancient astronomers saw points of light. We see cosmic time machines revealing not just where stars die, but when and what the universe was like as they did. The leap between these eras is staggering. Where observers in 1054 could only note brightness and color, modern astronomers track supernovas across multiple wavelengths: X-rays from shock-heated gas, radio waves from accelerating electrons, even gravitational waves from the collapsing core. SN 1054 left behind a nebula expanding at 1,500 kilometers per second. Today's distant supernovas show how that expansion rate has changed over cosmic history, proving the universe itself is stretching faster with time. The contrast isn't just technological, it's conceptual. Ancient skywatchers saw omens. We see physics laboratories testing relativity and nuclear astrophysics in conditions we could never recreate on Earth. Yet for all our advances, these explosions still humble us. The Crab Nebula's pulsar spins 30 times per second, a metronome of stellar death ticking since before the Norman conquest. Meanwhile, supernovas at the edge of observable space whisper secrets about an era when galaxies were infants, their light stretched and dimmed by cosmic expansion. From a star's death noticed by emperors to explosions rewriting the laws of physics, supernovas bridge human history and the cosmos' deepest mysteries, proving that sometimes the most fleeting events leave the longest legacies. The most frustrating part about studying ancient supernovas, we almost never get to meet the stars that birthed them. Imagine a detective arriving at a crime scene to find the victim's entire identity erased. No fingerprints, no dental records, just the aftermath of violence. That's what astronomers face when they spot a supernova billions of light years away. The explosion might blaze brighter than a galaxy for weeks, but the star that triggered it typically vanishes without leaving behind a single pre-explosion photograph. This isn't just an archival headache, it's a cosmic blind spot with real consequences. Knowing what kinds of stars produce which supernovas is like having a stellar genealogy chart, helping us predict how often these explosions occur and what they leave behind. Take Type 1 supernovas, the standard candles used to measure cosmic distances. For decades, astronomers assumed they all came from white dwarfs stealing mass from companion stars. Then Hubble spotted a peculiar outlier, a Type 1, in a galaxy with no signs of star formation, suggesting the white dwarf might have collided with another white dwarf instead. The discovery forced scientists to rewrite the rulebook, acknowledging that these critical distance markers might have multiple origin stories. The challenge gets even thornier with the most distant supernovas. When we look billions of years into the past, we're seeing stars that lived in a younger, more chaotic universe. Their compositions were different, mostly hydrogen and helium, with almost none of the heavier elements that modern stars inherit from previous generations. Did these purer stars explode differently? Did they leave behind different remnants without progenitor snapshots? It's like trying to reconstruct an extinct animal from a fossilized footprint. Occasionally, we get lucky. In 2005, the star SN 2005 GL's progenitor was caught on camera before it exploded, a yellow supergiant that defied expectations by being far less massive than predicted. Then in 2019, the doomed star Betelgeuse dimmed mysteriously, sparking speculation it might soon go supernova. It didn't, but the event gave astronomers front-row seats to a star's pre-explosion jitters. These rare cases prove how unpredictable stellar deaths can be and how much we still have to learn about the final years of a star's life. The James Webb Space Telescope offers new hope. Its infrared eyes can peer through cosmic dust to study stars in galaxies so distant their light has traveled for over 13 billion years. By repeatedly scanning these ancient neighborhoods, Webb might catch precursory signs, a star growing unstable, shedding mass, or heating up before its final act. Until then, every distant supernova remains both a revelation and a riddle, its origin story written in fire but missing the first chapter. What keeps astronomers searching is the tantalizing possibility that the first stars, those massive, short-lived giants born from pure hydrogen and helium, might have died in supernovas unlike anything we've seen today. Some theories suggest they collapsed directly into black holes with no explosion at all, while others propose they detonated with such force they scattered elements across entire proto-galaxies. The only way to know for sure: keep digging through the cosmic archives, one uncharted progenitor at a time. When a supernova explodes, it doesn't just unleash light, it fires bullets. Not the kind made of lead, but subatomic particles hurtling through space at nearly the speed of light, with energies so extreme they make Earth's most powerful particle accelerators look like toys. These are cosmic rays, and they're some of the most enigmatic travelers in the universe. Every second, about 100 of these high-speed particles zip through your body, their origins traced back to the shockwaves of dying stars millions or even billions of years ago. Picture the moment a supernova's shockwave rips through space, a supersonic wall of plasma moving at 30,000 kilometers per second. As this wave plows into surrounding gas and magnetic fields, something extraordinary happens. Electrons and atomic nuclei get caught in the turbulence, bouncing back and forth like pinballs between the shockwave's advancing front and the tangled magnetic fields behind it. Each collision adds another kick of energy, accelerating the particles to velocities just shy of light speed. It's nature's own particle accelerator, but instead of needing a 17-mile underground ring like the Large Hadron Collider, it uses the chaos of a stellar explosion to achieve energies 1,000,000 times higher. These cosmic rays don't just quietly fade into the void. They race across galaxies, weaving through magnetic fields for thousands, sometimes millions, of years before reaching Earth. When they finally collide with our atmosphere, they spark cascades of secondary particles, creating shimmering auroras of blue light detectable by specialized telescopes. Some are so energetic that physicists still struggle to explain their origin. The so-called "oh my God" particle, detected in 1991, carried the kinetic energy of a baseball pitch but packed into a single proton. If that particle had been visible, it would have appeared to move faster than light from our perspective, thanks to relativistic effects. But cosmic rays aren't just celestial curiosities. They've subtly shaped life on Earth. By constantly peppering our planet, they contribute to genetic mutations, nudging evolution along unpredictable paths. They also pose challenges for astronauts, as prolonged exposure to unfiltered cosmic rays can damage DNA, a major hurdle for future Mars missions. Even more mind-bending, these particles might influence cloud formation, with some studies suggesting they seed condensation nuclei in Earth's atmosphere, potentially altering weather patterns over geological time. What's truly incredible is how long these particles endure. A single cosmic ray can journey for billions of years, outliving the galaxy that birthed it, before finally smashing into a planet or dissipating into the cold expanse of intergalactic space. Every time we detect one, we're catching a whisper from a stellar cataclysm that might have happened before the sun even formed. A messenger from a dead star still hurtling through the universe, refusing to let its story end quietly. Not all stellar explosions leave behind a neat, spherical cloud of debris. In fact, most don't. Supernova remnants come in an almost artistic variety of shapes, delicate, lace-like filaments in the Veil Nebula, the ragged, bubble-like structure of Cassiopeia A, even the eerie, symmetrical rings of SN 1987A. These forms aren't random, they're cosmic fingerprints, revealing everything from the dying star's final moments to the turbulence of the interstellar medium it exploded into. Take the Crab Nebula, perhaps the most famous remnant. Its intricate web of glowing filaments traces the paths of shockwaves rippling outward at over 5 million kilometers per hour. But look closer and you'll notice it's not perfectly round. The nebula bulges slightly at the equator, stretched by the rapid spin of the pulsar at its heart. Meanwhile, remnants like the Jellyfish Nebula IC443 look like they've been shredded by invisible claws, their asymmetry hinting at uneven explosions or dense pockets of interstellar gas that slowed parts of the blast. Distance plays tricks on these shapes too. A nearby remnant like the Vela supernova remnant just 800 light-years away sprawls across 6 degrees of sky, letting us trace every twisted tendril of its structure. But observe a distant counterpart like the remnants glimpsed in galaxies millions of light-years away, and they often resolve into faint, blob-like smudges. Not because they're actually spherical, but because their fine details get compressed by perspective, like trying to admire the brushstrokes of a painting from across a football field. Some of the most bizarre shapes come from mixed morphology remnants, where X-ray and radio observations reveal structures invisible in optical light. Puppies A, for example, shows a shattered optical shell but glows brightly in X-rays at its center, a sign that the shockwave has plowed into a particularly dense cloud of interstellar material. Others, like the circles within circles of G291.0-0.1, suggest multiple shockwaves rebounding off each other in a celestial echo chamber. What's truly fascinating is how these forms evolve over time. Young remnants, those only a few hundred years old, often retain sharp, jagged edges from the initial explosion. But after millennia, the relentless push of the shockwave smooths them into more rounded forms, like pebbles worn down by a river. Except in this case, the river is the galaxy itself, its magnetic fields and gas currents sculpting the debris into shapes we're still learning to decode. Every twist, knot, and bubble in these cosmic wreckages tells a story, not just of how a star died, but of the invisible forces shaping the space around it. The violent death of a star doesn't just shine, it screams across the electromagnetic spectrum, broadcasting its demise in wavelengths far beyond what human eyes can perceive. While optical telescopes capture the dazzling visible light of a supernova, some of the most critical clues about these explosions come from the invisible realms. X-rays that pierce through debris clouds, radio waves tracing shock fronts, and infrared whispers from dust-obscured remnants. Each wavelength band acts like a different instrument in a cosmic orchestra, revealing aspects of the explosion that would otherwise stay hidden forever. Take X-ray observations, for instance. When a supernova's shockwave plows into surrounding gas at thousands of kilometers per second, it heats that material to millions of degrees, so hot it glows not in visible light but in high-energy X-rays. NASA Chandra X-ray Observatory has captured this phenomenon in stunning detail, like in the remnant of SN 1604 Kepler. The X-rays there outline a ragged bubble of ultra-hot plasma, its edges shimmering with the fingerprints of silicon, sulfur, and iron atoms forged in the explosion. Without X-ray vision, we'd miss these elements entirely, seeing only the cooler outer layers visible to optical telescopes. Then there's radio astronomy, which detects the supernova's echo long after the visible light fades. As the shockwave accelerates electrons to near light speed, those particles spiral around magnetic fields, emitting synchrotron radiation, a type of radio wave that can persist for millennia. The Vela supernova remnant, though 12,000 years old, still crackles with radiostatic, its tangled filaments mapping where the blast wave continues to energize interstellar material. For distant supernovas, radio observations are often the only way to track the explosion's expansion years later, since optical light dims too quickly across cosmic distances. But perhaps the most transformative window into ancient supernovas is infrared. When a star explodes in a dust-rich galaxy, much of its light gets absorbed by surrounding soot and re-emitted as infrared radiation, like sunlight warming a dark pavement. The James Webb Space Telescope excels at catching these heat signatures, allowing astronomers to spot supernovas completely invisible to Hubble. In 2023, Webb identified a supernova in the galaxy eMRG M0138, whose optical light was entirely blocked by dust, yet blazed brightly at infrared wavelength. This hidden population of explosions could rewrite our understanding of how often stars die in dusty stellar nurseries, especially in the early universe where such environments were common. The magic happens when these wavelengths combine. A supernova observed in X-rays might reveal its inner engine, the neutron star or black hole left behind, while infrared peeks behind dust curtains to measure the total energy released. Radio maps show where debris slams into interstellar gas, and gamma-ray detectors catch the most violent particle collisions. Together, they paint a fuller portrait of stellar death than any single wavelength could. It's like diagnosing a patient with X-rays, MRI, and blood tests simultaneously. Each test reveals what the others miss. Some of the most astonishing discoveries come from mismatches between wavelengths. In 2018, astronomers studying the supernova SN 2014C found its radio emissions brightened months after its X-rays faded, a clue that the explosion had slammed into a previously invisible shell of gas shed by the star centuries earlier. Without multi-wavelength observations, that stellar prehistory would have remained secret. Similarly, the supernova imposter Eta Carinea, a star that erupted in the 1800s but didn't fully explode, only reveals its true violence through infrared and radio data, showing vast dust lobes expanding at 6 million kilometers per hour. This spectral symphony isn't just about collecting data, it's about time travel. Distant supernovas whose visible light stretched into infrared by cosmic expansion often emit X-rays that, due to their higher energy, redshift less dramatically. By comparing these signals, astronomers can reconstruct how the explosion looked in its original, unshifted state, effectively undoing the universe's stretching effect. It's like listening to a song played through a warped record while simultaneously reading the sheet music. The combination lets you hear the music as it was meant to be. As telescopes grow more advanced, they're opening even stranger wavelengths for exploration. Some observatories now hunt for supernova neutrinos, ghostly particles that escape the collapsing core hours before light reaches the surface, while others chase after gravitational waves, the ripples in spacetime triggered by the star's final convulsions. These messengers complement traditional wavelengths, offering direct probes into the explosion's heart where even X-rays can't penetrate. The next great supernova in our galaxy might announce itself first through a neutrino burst detected underground, followed hours later by a blaze of gamma rays, then visible light, and finally radio echoes lasting centuries. What's clear is this: to truly understand a star's death, you can't just watch the fireworks. You have to listen to its full spectral scream, from the deepest radio growl to the highest X-ray shriek. Every wavelength holds a piece of the puzzle, and only by assembling them all can we read the full story written in stellar ashes. The supernovas whose light took billions of years to reach us didn't just fade away, they transformed, leaving behind ghostly remnants scattered across deep space. Picture one of these ancient explosions, its light finally arriving at our telescopes after a journey spanning most of the universe's existence. The star itself is long gone, Its debris field expanded so vastly that what was once a cataclysmic fireball is now little more than a wisp of gas stretched thin across dozens of light years. But don't mistake silence for absence. Depending on the original star's size, its remains could be anything from a neutron star spinning invisibly in the void to a black hole silently warping space-time around it. Consider the heavier progenitors, stars 20 times more massive than our Sun. When these giants exploded in the early universe, their cores likely collapsed into black holes, swallowing so much matter that not even light could escape. Today, those black holes might still lurk in their host galaxies, grown even larger by feeding on surrounding gas or merging with others. Some could anchor the hearts of quasars, blazing with energy as they devour matter, while others drift undetected, their presence betrayed only by subtle gravitational tugs on nearby stars. For slightly lighter stars, the aftermath could be a neutron star, a city-sized ember so dense it bends the laws of physics. Born spinning hundreds of times per second and blazing with magnetic fields trillions of times stronger than Earth's, these objects would have gradually slowed over billions of years, their radiation dimming to near invisibility. Yet some might still pulse faintly in radio waves, their beams sweeping the cosmos like lighthouse beams in an endless dark sea. Then there's the debris itself, the outer layers of the star blasted outward at unimaginable speeds. Over billions of years, that material would have cooled and dispersed, mixing with interstellar gas to form vast, faint clouds rich in heavy elements. In some cases, these clouds might have triggered new waves of star formation, their metals seeding future generations of planets. Others could have been shredded by galactic tides, their atoms scattered so widely they became indistinguishable from the background gas of the universe. But here's the haunting part: we may never know exactly where these remnants are now. The expansion of the universe would have carried their host galaxies farther away, stretching the space between us so much that their current locations are unreachable by any signal. The light we see is just a snapshot from an unfathomably distant past, like a photograph of a stranger who's already left the room. Yet even in their absence, these remnants shape the cosmos. The iron in your blood, the calcium in your bones, some of it might have originated in those very explosions, forged in stellar cores and scattered by forces strong enough to defy gravity itself. These distant supernovas didn't just die, they became part of the universe's endless cycle of creation and destruction, their echoes written into everything from the chemistry of galaxies to the DNA in your cells. So while their light has long since faded, their legacy lingers, written not in fire, but in the silent, invisible architecture of the cosmos itself. What if the most violent explosions in our universe aren't just cosmic spectacles, but portals to hidden dimensions? At the intersection of supernovas and multiverse theory lies a mind-bending possibility that these stellar detonations might be natural laboratories for exotic physics, their extreme conditions warping space-time in ways that could betray the existence of parallel realities. Imagine a supernova so powerful it briefly crumples the fabric of the cosmos, creating microscopic tears where the laws of our universe fray at the edges, a phenomenon physicists call quantum foam. In these fleeting instants, energy might leak into or out of other dimensions, leaving subtle fingerprints in the explosion's light or neutrino emissions. This isn't just speculative fiction. Certain hyper-energetic supernovas like the infamous SN 2006 JI defy conventional explanations. Dubbed superluminous supernovas, these events blaze up to 100 times brighter than normal, as if something is funneling extra energy into the explosion from elsewhere. One radical hypothesis suggests their excess power could come from interactions with higher dimensional space, where gravity leaks into our universe and turbocharges the blast. It's like tapping into a cosmic power grid we can't see but whose effects might be written in starlight. The smoking gun could lie in neutrino patterns. When a star's core collapses, it floods the universe with these ghostly particles, but if some neutrinos vanished en route to our detectors, Their missing energy might hint at brief excursions into extra dimensions before snapping back to our reality. Similarly, gravitational waves from asymmetric supernovas might carry imprints of higher dimensional geometry, like echoes distorting in a strangely shaped room. Even the afterglow of ancient supernovas could hide clues. Some theories predict that if our universe is a membrane floating in a higher dimensional bulk, then certain light particles, photons from ultra-distant explosions, might oscillate between dimensions as they travel, subtly altering their properties over billions of light years. Telescopes like the James Webb are now scanning for these anomalies, treating the cosmos as a vast particle collider where supernovas are the accelerators. Of course, not all physicists buy into multiverse explanations. Many attribute superluminous events to magnetars, neutron stars with apocalyptic magnetic fields, or collisions between stars and dense circumstellar material. But the beauty of extreme supernovas is that they force us to test the boundaries of known physics, whether or not parallel universes are involved. Their violence creates conditions so extreme that even wild theories become testable, if only we decode the right signals in their fading light. Perhaps the most poetic possibility is that every supernova is a two-way mirror. Just as we study their light for hints of other dimensions, beings in those other realms, if they exist, might detect our universe's supernovas as flickers in their skies, each explosion a fleeting handshake between realities. Until we know for sure, these stellar cataclysms remain both destroyers and messengers, their fury probing the very edges of what's possible. Discovering a supernova billions of light years away isn't just a triumph of technology. It's a testament to human persistence, late-night coffee runs, and sometimes sheer cosmic luck. Behind every distant stellar explosion in the record books, there's an astronomer who spent years staring at blips on a screen, waiting for the universe to blink. Take Saul Perlmutter and Brian Schmidt, whose teams scoured the cosmos for Type 1 supernovas in the 1990s. Their goal, to measure the universe's expansion. But what they found, dark energy, was so unexpected that Schmidt reportedly told his team, "We're either about to win a Nobel Prize or we've made a mistake so big we'll be laughingstocks." They'd spent a decade chasing faint smudges across thousands of telescope images, only to have the data append cosmology itself. Then there's the story of SN 2005 AP, the brightest supernova ever recorded until then. Astronomer Robert Quimby wasn't even looking for it. He was sifting through old data from the Texas Supernova Search when he spotted an anomaly others had overlooked. The explosion, located in a dwarf galaxy 4.7 billion light-years away, outshone its entire host galaxy by a factor of 300. Quimby's discovery wasn't just luck. It was the payoff for developing automated tools to scan terabytes of telescope data, teaching machines to recognize what human eyes might miss. Sometimes the human element is pure serendipity. In 2011, a graduate student at UC Berkeley named Peter Nugent was reviewing real-time data from the Palomar Transient Factory when he noticed a peculiar dot in the Pinwheel galaxy. It was SN 2011 Phi, a Type 1 supernova caught just 11 hours after explosion, the earliest ever detected. Nugent's quick thinking triggered a global alert, mobilizing telescopes from Chile to space to capture its critical first days. That split-second decision gave astronomers an unprecedented view of a supernova's infancy, like catching a firework the moment the fuse is lit. But not all discoveries come from high-tech surveys. In 2006, a Japanese amateur astronomer named Koichi Itagaki spotted a new light in the galaxy UGC 4905 while scanning the skies from his backyard observatory. The supernova, later named SN 2006 Jai, turned out to be one of the most luminous ever seen, a rare pair instability explosion possibly involving a star 200 times the Sun's mass. Itagaki's meticulous hand scanning of photographic plates, a method some professionals had dismissed as outdated, proved vital in catching this cosmic oddity. The emotional toll of the hunt is rarely discussed. Astronomers like Alex Filippenko, who's logged over 100 nights yearly at telescopes for decades, describe the grind of freezing mountaintop vigils, false alarms, and the heartbreak of cloudy skies ruining critical observations. One night in 2014, Filippenko's team at the Keck Observatory had mere minutes to confirm a distant supernova before sunrise. As twilight crept over Mauna Kea, they frantically adjusted instruments, knowing the next clear night might come too late. Their success SN 2014J in the Cigar Galaxy became one of the closest Type 1 supernovas in decades, offering unparalleled details about these cosmic yardsticks. What ties these stories together isn't just scientific brilliance, but the willingness to embrace uncertainty. Supernova hunters operate like detectives, solving a case where the evidence keeps fading. They balance cutting-edge algorithms with old-fashioned intuition, knowing that behind every dataset is a star that died before Earth formed, and when they succeed, the payoff isn't just data, it's standing at humanity's edge, catching whispers from the void that rewrite our place in the cosmos. The hunt for cosmic explosions is about to enter its golden age, not with incremental improvements, but with revolutionary leaps that will redefine how we see the universe's most violent deaths. At the forefront stands the Vera Rubin Observatory, poised to unleash an astronomical tsunami when it begins its 10-year legacy survey of space and time in 2025. This Chilean behemoth won't just scan the sky, it'll devour it, capturing entire hemispheres every few nights with a 3.2 gigapixel camera so sensitive it could spot a golf ball on the moon. Where current surveys might catch a few hundred supernovas annually, Rubin could net millions, spotting stellar explosions across 11 billion years of cosmic history with mechanical precision. But Rubin's true magic lies in its tempo. Most telescopes stumble upon supernovas by chance or through targeted searches covering tiny sky patches. Rubin will watch the entire visible southern sky every 3 days, creating what astronomers call a celestial movie, a time-lapse so comprehensive it'll catch supernovas within hours of detonation, even at redshifts above 3. Imagine catching the universe's first stars in their death throes, their light stretched from ultraviolet to infrared by cosmic expansion. Rubin's rapid-fire observations mean we'll witness these explosions unfold in unprecedented detail, from shock breakout the moment the blast first tears through a star's surface, to the critical early phases when key elements form. The revolution doesn't stop there. NASA's Nancy Grace Roman Space Telescope, launching around 2027, will combine Rubin's wide-field vision with Hubble's razor-sharp resolution, plus an infrared gaze piercing through cosmic dust. Where Rubin maps the sky, Roman will zoom in like a cosmic macro lens, dissecting supernova chemistry in galaxies so distant their light predates Earth's formation. Its coronagraph instrument might even spot the faint glow of pre-explosion stars, solving the progenitor mystery that's plagued astronomers for decades. Together, these telescopes will form a tag team, Rubin sounding the alarm for new explosions, Roman delivering forensic close-ups. Meanwhile, the European Southern Observatory's extremely large telescope will bring 40-meter mirror firepower to the hunt. When fully operational, its Harmony spectrograph could analyze light from supernovas so distant their host galaxies appear as faint smudges in other telescopes. By splitting that light into ultra-high-resolution spectra, it'll reveal trace elements in the debris, not just confirming a supernova's type, but pinpointing exactly how much nickel, silicon, or titanium was forged in the blast. That chemistry holds clues to the star's mass, rotation, even whether it had companion stars before exploding. Yet the most transformative tool might be artificial intelligence. New machine learning algorithms are already sifting through Rubin's precursor surveys, identifying potential supernovas minutes after detection, far faster than human scanners. Future systems won't just flag explosions, they'll predict which merit urgent follow-up based on real-time light curves, filtering routine events from cosmic oddities like pair instability supernovas or possible quark nova candidates. It's like having a tireless assistant who knows exactly when to shout, "Drop everything." This one's different, and the targets, beyond just increasing numbers, these telescopes will hunt supernovas in unexplored cosmic eras. The universe's first star's population, 3 likely died in explosions without modern equivalents, their pure hydrogen and helium compositions producing bizarre physics we've never observed. Rubin and Roman could spot their remnants by searching for ultra-distant supernovas with abnormal light curves or element signatures. Other teams planned to chase failed supernovas, giant stars that collapse directly into black holes without visible explosions, detectable only through sudden vanishing acts in time-lapse surveys. The data deluge will demand entirely new ways of working. Astronomers estimate Rubin alone will generate 20 terabytes nightly, enough to fill 20,000 DVDs every evening. To cope, teams are building automated pipelines that'll analyze supernovas in near real time, flagging anomalies for global telescope networks to investigate. Citizen scientists will play a role too, through projects like Zooniverse, where volunteers help classify oddball explosions algorithms might miss. This isn't just more astronomy, it's astronomy at warp speed, where discoveries move from telescope to preprint archive before the coffee in an observer's mug goes cold. What awaits in this avalanche of new supernovas? Possibly answers to cosmology's biggest puzzles. By comparing ancient explosions to modern ones across unprecedented samples, we could finally nail down whether dark energy's strength changes over time. Some theorists even speculate we'll find supernovas behaving differently in the early universe, their light curves distorted by alternative physics or extra dimensions. Others hope to catch a supernova's gravitational waves alongside its light, combining signals to probe the explosion mechanism in 3D. One thing's certain, the next decade will rewrite the supernova playbook. From stars that vanish without a trace to hyper-energetic blasts defying known physics, each new discovery will peel back layers of stellar life and death we've only theorized about. The cosmos has been broadcasting these cataclysms for billions of years. Thanks to these telescopes, humanity is finally tuning in with perfect reception, ready to hear every note in the universe's symphony of destruction. Supernovas occupy a strange space in human imagination, simultaneously real and mythical, grounded in astrophysics yet sparking stories that stretch far beyond science. Hollywood has long exploited their terrifying grandeur, from the shockwave that threatens the USS Enterprise in Star Trek to the apocalyptic stellar explosion in 2012 that wipes out civilizations. These cinematic portrayals often exaggerate the science. No, a supernova wouldn't vaporize Earth instantly from thousands of light years away, but they capture something primal, the awe of cosmic power dwarfing human existence. Even The Martian nods to supernova risks, with astronaut Mark Watney joking about radiation exposure, a rare case of Hollywood acknowledging the real but slow-moving threat of cosmic rays from ancient stellar explosions. Literature dives deeper, using supernovas as metaphors for transformation. In Arthur C. Clarke's The Songs of Distant Earth, the impending destruction of Earth's sun forces humanity to flee, framing the supernova as both doom and rebirth. Meanwhile, sci-fi author Alastair Reynolds imagines hyper-advanced civilizations harnessing supernovas as energy sources in Revelation space, turning stellar death into engineering. These stories reflect an unshakable truth. Supernovas don't just die, they feed the universe, a duality artists and writers have latched onto for centuries. Visual artists, too, bend supernova imagery to their needs. The swirling, fiery nebulae in Van Gogh's The Starry Night eerily resemble modern Hubble images of supernova remnants, though the painter had no knowledge of them. Contemporary installations like Katie Patterson's Earth Moon translate supernova light into Morse code, blending art and astronomy. Even music channels their energy. The band Muse titled an album Supermassive Black Hole, but their soundscapes mirror the crescendo of a stellar explosion, chaotic, luminous, and unforgettable. Perhaps the most fascinating cultural twist lies in video games. Destiny 2, Whisper of the Worm mission unfolds inside a frozen moment of a supernova, capturing the explosion mid-blast, a poetic nod to how these events stretch human perception of time. Indie game Outer Wilds goes further, weaving an entire mystery around a looping supernova, forcing players to confront the inevitability of cosmic cycles. These interactive narratives get closer than any textbook to making stellar death felt, not just understood. Yet for all their dramatizations, pop culture occasionally stumbles onto eerie truths. The Doctor Who episode, The Rings of Akhenaten, features a planet system orbiting a dying star uncannily similar to real-life pulsar planets discovered orbiting stellar corpses. And Interstellar's Gargantua black hole, while fictional, mirrors how supernova remnants warp spacetime. The line between science and fiction blurs when imagination aligns with the universe's own creativity, proof that sometimes reality outdoes the myths. What ties these portrayals together is humanity's need to personalize the cosmos. Supernovas, especially distant ones, are abstract until stories give them stakes, lost homes, ticking clocks, or last-ditch escapes. They become more than physics, they're reminders of our fragile, fleeting place in a universe where stars live and die on scales we can't fully grasp. Whether as backdrop or catalyst, supernovas in culture always whisper the same question. If something so magnificent can vanish, what does that mean for us? And perhaps that's why these explosions endure in art long after their light fades from the sky. They're the ultimate symbols of beauty and impermanence, fireworks too brilliant to ignore, too vast to comprehend, and too brief to hold. Every painting, film, or novel featuring them isn't just borrowing a scientific phenomenon. It's trying to cage a piece of cosmic wildfire, if only for a moment. At the edge of observable space, where starlight stretches into whispers, distant supernovas aren't just dying stars, they're cosmic Rosetta Stones, decoding the universe's deepest mysteries. Every explosion we spot billions of light years away does more than dazzle, it rewrites textbooks. Take the universe's expansion rate, for example. Before the 1990s, astronomers assumed gravity would slowly break cosmic growth like a bike rolling uphill. Then distant Type 1, supernovas revealed the opposite. Space wasn't just expanding, it was accelerating, propelled by some unseen force we now call dark energy. Without those faint, faraway stellar blasts, we'd still be oblivious to the invisible hand shaping everything. But expansion is just the start. These ancient explosions act as time capsules, preserving snapshots of the universe's chemical adolescence. When we analyze light from supernovas that detonated before Earth formed, we're sampling the cosmos's elemental recipe in its youth. Surprise, even back then, heavy elements like iron and silicon were already abundant, proving stars lived fast and died furious in the early universe. That changes how we model galaxy formation. Turns out, the first stellar generations didn't just sprinkle metals into space. They blasted them outward like cosmic shrapnel, jump-starting planet building sooner than anyone guessed. Then there's dark matter, the universe's elusive scaffolding. Distant supernovas help map its distribution through gravitational lensing. When a supernova's light warps around unseen mass, the distortion reveals where dark matter clumps, like tracing wind patterns by watching leaves swirl. Some ultra-far explosions even appear oddly magnified or duplicated, their light bent by invisible structures we'd never detect otherwise. It's like using stellar fireworks to X-ray the cosmos's hidden skeleton. The grandest question of all, the universe's fate. Will expansion tear galaxies apart, leaving skies eerily empty in 1 trillion years? Or will dark energy's grip weaken, allowing gravity to pull everything back into a fiery crunch? Distant supernovas are the only yardsticks long enough to measure these slow-motion trends. By comparing explosions from different epochs, some ancient, some recent, we've caught dark energy subtly strengthening over billions of years. That chilling clue suggests a lonely, cold future where galaxies vanish over the horizon, their light stretched beyond detectability. Supernovas won't just witness that fate, they'll have predicted it first. Yet the most profound gift of these stellar messengers might be humility. When Hubble spotted SNUDS-10 WIL, we weren't just seeing a star die 10.5 billion years ago, we were glimpsing a universe so young galaxies hadn't finished assembling. That explosion's light began its journey when Earth's atoms were still scattered across nebulae, unformed. Every distant supernova is a mirror reflecting our own insignificance and our astonishing luck to exist in the narrow sliver of time when the cosmos is transparent enough to see them, yet dense enough with stars to make life possible. So why do these far-flung cataclysms matter? Because they're the universe's way of keeping a diary. Each explosion records the conditions of its era, the pull of gravity, the push of dark energy, the chemistry of nascent galaxies. Without them, we'd be adrift in a sea of questions, guessing at origins and endings. With them, we're detectives piecing together the greatest story ever told, how everything came to be and where it's all heading. The next time you look up at a seemingly still night sky, remember, it's alive with silent fireworks, each one a beacon not just of destruction but of understanding. From the ashes of dying stars to the birth of elements that shape our very existence, these 30 mind-blowing facts reveal how distant supernovas serve as cosmic lighthouses, guiding us through the universe's greatest mysteries. We've journeyed across billions of light years, witnessing explosions so powerful they outshine galaxies, and so ancient their light predates Earth itself. These stellar cataclysms aren't just fireworks, they're time machines, carrying snapshots of the universe's youth when galaxies were raw and untamed. They've exposed dark energy's relentless push, mapped invisible dark matter, and even hinted at physics beyond Einstein's wildest dreams. Every iron atom in your blood, every calcium molecule in your bones was forged in their fury, scattered across space by shockwaves that still echo today. But the real magic lies in how these discoveries connect us to the cosmos. When you gaze at the night sky, you're not just seeing stars, you're seeing the aftermath of supernovas that died long before humans walked the Earth, their light finally reaching your eyes like messages in a bottle from the distant past. The same forces that shaped galaxies and seeded planets with life now fuel our curiosity, driving telescopes deeper into the unknown. And with every new supernova spotted at the edge of observable space, we're handed another piece of the puzzle, whether it's a star that defies known physics or a remnant that rewrites stellar evolution. So what's next? The universe hasn't run out of secrets, and neither should we. Grab a telescope, step outside on a clear night, and let your eyes wander. That faint smudge might be a galaxy where supernovas are brewing right now, or the ghostly glow of one that vanished millions of years ago. Dive deeper into the science behind these explosions, follow the latest discoveries from observatories like James Webb, or simply marvel at the scale of it all. Because every time we look up, we're not just observers, we're part of the story. A species learning to read the universe's diary, written in starlight and fire. The cosmos is speaking. Are you listening?